and you look like you're enthralled there. You know. Okay, all right. Okay, so solving for these variables that happen to be powers. And we're still doing our change of form, going from exponential to log or from log to exponential. That's the key component. Have you noticed that that's been the key component of this whole chapter? If I don't know how to change from one to the other, I'm in trouble. I don't want to do that. So we recognize that this is an exponential form, and we want to change it to our log form. So let's buy an elephant, right? Did I do that right? Well, here's what I think that they were explaining to me. Were you telling me? Okay. Let's L B by an exponent elephant. Let's buy a xylophone. Oh, he did an E right here? Oh, that would be creative. That would be creative. Let's buy an elephant. Buy an elephant and. People might see the BE and think B. As in to be, or not to be. That's the question. Yes. Alright, so if you like it, let's buy an elephant with the actual E in there instead of the exponent elephant, then you go right ahead and think about that. Jeez Louise, what a tough crowd. So we're going to go and make this become log base 3 of 0.7 is equal to negative x. And now this is where the change base formula comes in. Remember that when you set it up in the calculator, you have to be careful that you set, first of all, 2 logarithms. And if you're going to try and put it in the calculator once, after you do log 0.7, make sure you close that with a parenthesis. Close it. And then hit the division button, and then do log 3. And you're going to tell me that the answer is negative, I believe, if I got this right. 0.32, is that right? So that means x is equal to 0.32. So there we go. So that's the stuff we have been doing. We were doing it kind of cheating way. We were doing change-based formula before we actually looked at change-based formula. Remember, the other way to solve these would be graph it, trace, or just trial and error. I can do that as well. Now, this next one here, there are 2 approaches to this. One is to, well, first of all, change the form. So somebody change the form for me. What's it look like? Log base 3 of 9 cube root of 3. Okay, now, some people are going to see that.
I would change it.
You what?
I would change it. I wouldn't make it long. 3 to 3 over 9. 3 to 3 to 9.
You change.
No, that's not squared.
Yeah, that's not being cubed. Yeah, be careful there. Does anyone recognize what you could do right here? Properties, think properties. What's happening right there?
You could make the 9 3 squared.
Well, you could do that. Yeah, I could make the 9 3 squared. Yeah.
3 to the 1/3.
And a 3 to the 1/3. Yeah, could do that too. So they're saying, here's what you could do. You could do log base 3 of 3 squared times 3 to the 1/3. What does that become? 7/3, right? All right, you could do it as log base 3 of 3 to the 6/3 plus 1/3 is 7/3 equal to x. Yep, so then you can see this as, let's change it out of log form back to exponential. Because now I have a log set up to solve for x, right? Which is what logs do anyway. So we have 3 to the x. Whoa.
Yeah.
Whoa now. Hello. 3 to the x equals 3 to the 7/3, which means x is equal to 7 over 3. Which is what? 2.33, right? Now there's another way to do it, using properties of logarithms. And that is to recognize that 9 times cube root of 3 is a product property. And it can be separated into log base 3 9 plus log base 3 of cube root 3. So here, let's move this guy in. So we have log base 3 of 9 plus log base 3 of cube root of 3. It's still just in the numerator. And then I've got a product, I've got a power going on right there, so I've got now log base 3 of 9 plus log base 3 of 3 to the 1/3, which becomes a log base 3 of 9 plus a 1/3 log base 3 of 3. Then all of that would be divided by log base 3 of something. What is it? No, it's not divided by n. Wait. I lost something. Wait.
What equals x?
Oh, yeah. I don't know why I have that. Why did I have that? Hang on here. So this is what equals x right now, and then let's see if we get the same thing. So somebody can do. So I have some change basing going on right here. I got a log base, or a log base 10 of 9 over log base 3 plus 1/3 of log of 3 over log of 3. It gives me the same thing. That's a lot more work, right? Well, if you're just feeling like you're want to work on properties, there we go. Good grief. Yeah, so over that 1/3 times log base 3, whatever that number is, would have to be divided by the log. All right. Anyway, since you love that one so much, let's skip these next two. But if you did them, that's great. Good job. Way to go. And let's get to the next one. Half-life. Carbon 11 is 20 minutes. How long will it take for 800 grams to kill? We've seen problems like this, haven't we? Yes, we have. And remember, we can set these things up depending on how I look at this. I look at this where generically we're talking about this equation, right? A of t, A sub O, 1. Now, because we have a half-life, I know it's going to be minus r to the t, where t in this case is every 20 minutes. So my time period is 20 minutes. So this is a setup where I'm not looking for a per minute change, but a per 20 minute change. But did we have an equation that allowed us to go to a per minute change? Yeah, we have the BT BTK problem, right? The BTK was the one that was saying we have A sub O, B to the 1 over K to the T power. And this is a per minute change versus a per 20 minute change. And the K is the time it takes to, in this case, we're halving our original amount. So remember the BTK problems happen when you were looking for a change to the original amount. Change to A sub O. And then a period that tells us how long that happens. So we would know in this problem that if we have a half-life, that's our B. And then it's doing a half thing in every 20 minutes, so that's our K. 20 minutes. You can use the first one. We'll do both. We'll see what happens. So we'll do the first one. We'll go back to the old school. Let's just talk about what happens if you're going to go every 20 minutes on this problem. Let's try it for the 640. What would it look like? So we're looking for how long does it take to go from 800 to 640 grams. We know that A of t, the final amount, is going to be 640. We started with 800. And then my 1 minus r is our growth factor, or in this case, a decay factor of 1/2. Right? So what we're going to find here is the number of 20-minute time periods that we're going to end up with. So this is we get 0.8. It's equal to 1/2 to the t power. And then I set up my change base type thing. I get log basically 1/2 of 0.8 is equal to t. Now I have log of 0.8 over log of 1/2. No, we don't know t. No, it's asking you for how long will it take. So we're looking for t. So this would then say that t is equal to the log of 0.8 over the log of 0.5. So somebody give me this number. What? 0.32?
Yeah.
Okay, now that's 0.32. That's the number of time periods. That's not our answer. That's just how many time periods. So we have 0.32 of a 20-minute time period. So I know that I have that answer. Remember, this is every 20 minutes. So I have 0.32. What are we going to get there? 0.64. I have 6 point what? 6.44 minutes. Is that right? Are those numbers right, you guys? Okay. So again, that's not counting it per time. That's going per 20-minute period. I would be an advocate for going and thinking about a BTK for this problem because I knew that I was changing my initial amount by half, and I was doing that in a 20-minute period. So let's see what the difference is setting it up that way. So then we're going to have A of t is equal to A sub O, B to the 1 over K, T, still 640, still 800, but then I have 1/2 to the 1 over 20 to the T power. So now this is a per minute change instead of a per 20-minute change. We're going to see our answer is going to be different. So I get 0.8. Somebody, what's 1/2 to the 1/20th power? So that's a rounded value, right? 0.97. And it keeps going probably? Is it like a terminating decimal? Does it look like it doesn't? So it looks like it's an irrational number. All right. So we're going to round it, which is going to change our answer. Going to adjust it a little bit. And then here we are with changing my, I have log of 0.97 of 0.8 is equal to t. So now what's my answer? 7.33?
Yeah.
Is that right? You guys agree? Log of 0.8, close it, divided by log of 0.97. So there is a difference between me setting it up on a per minute change versus a per 20 minute change. Which one's right? What do you guys think? Which one's right? Let's say you're being conservative. Which number would you want to take? I want to take the 7.33. So again, per minute change versus a per 20 minute change. Now technically, both of these process for the same. I mean, we're not wrong per se here, but I'm going to be again. I'm going to say go with the BTK one. Break it down per 20 minutes. Yeah. Oh yeah, so when somebody did this, was this exactly 0.32 or was that also rounded? Rounded. It was rounded? So see, every time you do these rounding things, I'm going to give myself the possibility of increasing this margin of error. So what I would recommend doing is, if you can, whenever you take these log values, just keep them in the calculator. Log of 0.8, you got the answer. Then hit the divide button, and then do log of 0.97, and then you can get a more exact answer versus rounding. I think when we worked this out in the third period, it was like 4.5 or 4.4 or something like that. So it's different because they rounded it as well. So. But if your process is set up, and if you had set up the block equation and you made the statement, I'm going to use my a sub t equals a sub o 1 minus rt because I know that t represents every 20 minutes. Or if you set up the red equation, you're good. I do. In fact, there are a few of you, two, that set up one of our quiz problems with the 20-minute time period type setup versus a BTK setup. And you were right. Right? Questions? Yes.
You could use either equation.
What did I suggest?
Also be
Conservative. All right. Here we go. I'm not going to do anything with this other than let's talk through the answers real quick. I think that was the only problem we had back there. Oh, we didn't do the 40 one, but and so how do I solve for A? What do I do? No, I don't cube root. Don't even need to change it to log form. Don't go back and just start being, oh, we're in log chapter, that means I need to use a log. Don't be the robot. What do? Undo a power of 4. We don't cube root to undo a power of 4. We take a fourth. No, you didn't. You said cube root. Did she say cube root? She said cube root. There we go. We're going to do that. So somebody tell me what is the cube root of 62? 2.8. The fourth root. Dang it! 2.81. How do you take that on the calculator? The calculator probably has a button that looks like this somewhere. And then I bet your calculator would mean you have to put the 4 in first, and then hit that button, and then hit 62. We'll look at it. All right, how about B? What's the answer for B? How do we do B? Now we set it up as a logarithm because we're looking for an exponent. Log base 4 of 81 is equal to, whoops, is equal to x. So changing log of 81. Say it again, x equals what?
3.169925001.
Okay. 17. Thank you. All right, and then this next one, this is just a